Phantom types are a powerful way to let us give the Swift compiler more information about our code. In this video, I'm going to walk you through why you'd want them and how they work, and most importantly, give you lots of sample code you can try for yourself. Now, this long video is actually a free sample from my Hacking with Swift Plus program, which you can find out more about up there, hackingwithswift.com/plus. There I post subscriber-only videos going in real detail about topics like this one, all in Ultra 4K HD video over there at least, plus articles, code, and more. There's lots to check out at that URL. Go and have a look. Here, I've got a simple macOS terminal project, a great place to just noodle around without Swift UI or UIKit or similar. Just plain old Swift code. And the basic definition of a phantom type is this: some generic type that does not use at least one of its generic parameters. That's it. And when you see the code, you're like, that's easy, it's obvious, but you're not quite sure why. We'll come on to that. First things first, let's do this example code of what a phantom type looks like. I could say there's a struct employee that is generic over some kind of role and conforms to the equatable protocol. And inside there, I'll say there is one property called name, which is a string. And that's it. So it's generic over some kind of role and conforms to equatable, but does not use that generic type parameter, the role, inside the type itself. And the type definition is just a string, right? And that is a phantom type. That's it right there. It's that simple. And you're thinking, why the heck would you want that? I get that. I understand that entirely. We'll come on to that in just a second. This is different from regular generic types. Like in Foundation, there's a type that looks like this, struct measurement, that's a generic over a unit type. And it has a unit type and a value double, something like that. That's the measurement struct more or less from Foundation. There's some more code behind it, but that's the basic of it. That is a regular generic. That's not a phantom type. You can see it's generic over a unit type, and that is used in the definition right there. So it is not a phantom type. So the definition is real simple, right? We're generic over something, role, but we aren't using it. It's a string here. So the real question is, why the heck would you want that? What does that give us? So we could very easily say, well, actually, if it's struct employee and we aren't using role, boom, make it not generic. Same result. Not quite. There's an important difference. Although we don't really use the parameter here, it's not used at all, Swift knows about it. Swift will enforce the rules for us, having an extra bit of complexity there. Swift knows about it, and that's important. For example, if you worked for a software company, and there you had programmers and you had salespeople, and they're both employees, but they're different kinds of employees. You wouldn't want programmers doing sales, hopefully, and you wouldn't want sales doing programming, at least not in this company. We can represent this difference with a no-case enum. We could say there's an enum sales and an enum programmer. Boom. To differentiate between sales and programmer. Now, it's a good idea to use a no-case enum rather than struct sales and struct programmer, because you can make a sales when it's a struct. You could say, let Sue equals sales and make an instance of that type. Whereas if it's an enum, that isn't possible anymore. So you're making it clear to the other developers and yourself for the future, quite frankly, that this is not designed to be made. So it's an enum with no cases like this. Now, let's say you had a friend called Zoe who worked in the coding team for your company. You could represent her in the code by saying this: let Zoe1 be equal to employee programmer with the name of Zoe. And if you had another friend, also called Zoe, who worked in the sales team, you could represent her by saying this: let Zoe2 equals an employee in the sales team, also with the name of Zoe. Now, we've made employee conform to equatable, which means the Swift compiler will synthesize for us an equals function to compare employees. And it will compare them line by line for their properties. So here it's name, so it'll do is name equal to name. So we should be able to say this. Print Zoe1 is equal to Zoe2. And that's great. Except, boom, we can't. We cannot compare those two things anymore because we are no longer comparing an employee against an employee. We're comparing an employee programmer against an employee sales. And Swift's telling us these aren't the same type anymore. So even though we aren't using the type, Swift understands. Swift stops us from compiling. Swift thinks these two are different. You shouldn't compare these two things. If we had, in comparison, made the role a property, if we'd said, var role was a string, and then made it up here, just regular employee, we might say you are an employee with the name Zoe and the role of programmer, and then employee sales with the name role of sales. The difference is marked. The code now compiles, and at runtime, yes, they're different. I'll return false. One is a programmer, one is sales. It'll compare the role and say they're not the same. But the code now compiles, and that's the power of phantom types. We are giving Swift extra information that clarifies how things should work and allow it to work harder on our behalf. And when done well, it's going to allow logic errors to surface as compiler errors. You've made a fundamental mistake. Swift will literally not allow you to build your code because you're trying to do something that doesn't make sense, which is great. Now, let's look at some other examples to give you more flavor for this. If you're working in a hospital that handled blood samples, you're analyzing blood samples perhaps, you might start by defining some of those possible blood types. I won't do all of them, just some. You might say there's an enum of O positive, like this, and an enum of A positive, and then an enum of B positive. And there are more. And now you can define a blood sample struct that's generic over some kind of blood type, like this. Struct blood sample, generic over type. Let amount be a double. And then, because we can, we'll add some operator overloading. We'll say static func plus LHS is a blood sample, RHS is a blood sample, and returns a new blood sample. And we'll just say there's a new blood sample with the amount being LHS.amount plus RHS.amount. Add the two blood samples together. And it's got this plus operator here, so we can combine blood samples. We can say, well, we've got 5 mils here of O positive and 10 mils here of O positive. It's just O positive, put them together. But Swift now understands that two samples from different blood types are different and stop us from making mistakes. So, for example, we could say, let sample 1 be a blood sample of O positive, with the amount of 5 mils. Then let sample 2 be a blood sample of A positive with the amount of 5 mils again. And let sample 3 be a blood sample with O positive again. And we'll do amount of 7 mils. Boom. And so now this code will work. Let combined 1 equals sample 1 plus sample 3. It knows they're both O positive. That's okay. It can do that. But we cannot say let combined 2 equals sample 1 plus sample 2. Because they are different blood types. And they're different things. You cannot mix blood types like that. It doesn't work like that. That's going to actually hurt somebody, if not kill somebody, giving that kind of infusion to somebody. So Swift now understands this is not a good thing. Do not allow us to mix these types. Sometimes the differences are less subtle. For example, if we had a struct user and we had let ID int and let age int. So two integers like this, and they're both plain integers, so there's nothing stopping us from saying let user equals a user, ID 53, age 53, and then do print even user.id is equal to user.age. That's valid code. They're both integers. Of course you can do that. And yes, they're identical. That's going to print true. But if you are comparing user IDs to user ages or user shoe sizes, you've almost certainly made a logic error. That makes no sense. And it's a mistake that phantom types can catch for you. That's the point of them. So again, first you make no case enums. We're going to say there's an enum of user ID. Come on, user ID. There we go. And we'll do enum of age, like that. And next we make a struct that's generic over some kind of type, like this. We don't care what, but something. So we'll say struct tag is generic over type and is equatable. Var value int. So it's going to hold a single integer, but it's tagging it somehow. And now we can modify our user struct. We can say that ID is not an int anymore, it's a tag of user ID. Like that. And age, that is a tag of age. And we can now initialize that with integers directly for ease of use. ID int, age int, self.id is equal to tag of value ID. Self.age is equal to tag value is the age, like that. And now trying to compare ID against age makes no sense. Swift understands it is not a good idea, don't do that. Now in practice, I'd probably rejig this slightly. I'd probably say, let's make tag conform to the expressible by integer literal. And then add the initializer for that, which is init with integer literal value, integer literal type, self.value equals value. So I'd have that conformance instead, because now that allows Swift to make these tags for us directly from an integer, which is nice. So we can get rid of this whole code up here and let Swift synthesize that for us, which is a much, much nicer way of working. It still won't compile, of course, because it's still tagged, but at least the concept is now simpler, which is great. Now, for a broader solution to this same problem, I've got an article about this called Improving Your Swift Code Using Value Objects. I'll link to it down below. Have a look there for that. But the most important thing to remember here about phantom types is that they're empty. That generic parameter isn't used. There can be more than one if you choose to. And the Swift compiler is fully aware of them anyway. It takes them into account in its comparisons and its synthesized methods and so forth. It understands what they are. And that means you can use them as constraints and extensions and more. They're really powerful. Now, there are lots of practical ways you can use phantom types to build interesting stuff. And I came across one fascinating experiment from Suresh Kanlu. In his example, Suresh uses phantom types to build a state machine where invalid transitions cannot compile. Swift will not allow it. Now, state machines are pieces of code that are designed to move between a series of predefined states. For example, a vending machine might say, I'm waiting for a customer, first state. Then a coin's been inserted, second state. Then fetching selection, the third state. And then serving selection, the fourth state. And it moves from A to B to C to D, then back to A again. And this is nice because you can't go from waiting for customer to serving selection, because you haven't had a coin inserted in there. You haven't had fetching selection happen as well. So you don't want to go from A to D. Now you could do that, of course, with fatal error or whatever you want to in your code. But with phantom types, we can actually encode that into the compiler so that invalid transitions don't compile. Now, Suresh very kindly gave me permission to use this example code here. I'm going to simplify it a little bit because I want to focus on the part that really matters. So let's have a look at that now. Let's go into here. First, we're going to define the states our machine can be in. And for this example, we'll have the four that define a vending machine. So I'll say there's an enum waiting. We are waiting for a customer to come along. Enum coin inserted. The money's in the slot. What do they want to order? Then enum fetching. We are now looking around for the item. And then enum serving. We are serving the item to the customer. Second, we're going to make a phantom type that stores a transition between any two states, from state to state. That's what it does. So we'll say there's struct transition from to and be empty. It uses neither of those generic type parameters. They're neither use, so it's a especially phantom type. And that's fine. The struct's literally empty, but that's okay because Swift's able to look at those types and understand what they mean. Third, we'll make a machine struct that represents our state machine in any one given state. And this is going to have a single method to transition between the current state to a new state. So we'll say struct machine generic over state. Then func transition to a new state with transition, and this is going to be a transition from that state to a new state, and return a new machine to the to state, like that. Inside here, I'll just do init, send back the correct machine. Now, that's hardly any code. That's not a lot of code at all, but it's quite dense. So let's have a look at it in detail. This machine struct is generic over some kind of state. And this transition method is generic over some kind of to state. But it also uses the state from the machine struct, like that. And so we're saying it has to go from wherever we are currently to some other kind of state. And it'll return a new state machine that its current state is the to state. So the new machine has its current state set to the new state. And then using .init here means to send back the new machine, which is fine. Now we can go ahead and define all the valid transitions for our vending machine. So we're going to say let start equals a transition from waiting to coin inserted. So the customers put their money in the slot. Coin insert id. Let selection made even, be a transition from coin inserted to fetching. Then let delivery be a transition from fetching the item to serving the item. And let reset, when it's all gone through, to be a transition from serving back to waiting. Boom. And that's it. That's our entire state machine defined. That's all the code it takes. And it's quite brilliant. We can now create a machine with a particular state. We could say, let M1 be a machine of type waiting. And we can step through to other possible valid states. We could say, let M2 be M1.transition with start. Move to the start state. A coin's been inserted. And then we'll do let M3 equals M2.transition with selection made. Then M4 be M3.transition with delivery. Let M5 be M4.transition with reset. And they're all valid states. And the magic here is that Swift will check all those transitions at compile time to make sure they're valid. It's just not possible to make an illegal state. So if I had let M6 be M5, which is a machine in the waiting state, as you can see, dot transition with delivery, try and deliver before a coin's been made or a selection's made, boom. It's saying you can't do that. It is not possible to do that with your machine, which is brilliant. I think this is a fantastic experiment because it shows us how we can leverage the Swift compiler to prove that our code is correct. It's proving our code is correct. It's saying you cannot do that. It's wrong code. It's not allowed. I think it also makes a fascinating exploration of phantom types in action. However, in practice, this solution doesn't work so well. And to explain why, I asked Sarouche himself. Here's what he said. I originally wrote this as an experiment to see if I could have the compiler protect me from performing invalid transitions on a state machine. But I quickly realized that changes to the state would cause the type of the entire machine to change, meaning that it couldn't be stored back into the same variable. This prevents you from having it as a property on, say, a view controller, with transitions modifying the state machine. So, fun to try out, a little impractical in actual usage. Now, before I finish, there's one more technique I want to demonstrate, and it's quite different from all the earlier examples. Let's clean up our code. It's this piece of code. Func undefined t. Takes some sort of message string, equal to nothing by default, and returns a t, and we'll do fatal error, and then we'll do undefined message. Boom, like that. Now this is not a phantom type, but it is a great example of using Swift's type system in interesting ways. And I first saw this being used in a talk by Johannes Weiss from the Swift Neo team, where he presented this idea as a useful global function to have around your code while you're still building your app. And this function, undefined t, can act as pretty much any other kind of value you like because it's generic over t. It'll do anything. And it'll return the t. But inside, of course, it doesn't really do that. It's not actually used inside the function. But fatal error returns never, a special type, which means this code will never return. So Swift understands it hasn't got to really return a t, which is great. So that allows the code to compile and be used. And this setup is brilliant because it allows it to work as a placeholder in your code, just to make your code compile while you're busy doing something else. You're doing 2 or 3 things at once, and you'll come back to this in a minute, but just for now, you want your code to compile cleanly. Undefined is great for that. You can just fill in vacant parts, and it'll just work as a placeholder for the real thing. And you can use it however you want. You could say, let name be a string. I'll use undefined example string. That's fine. Or let score int be an undefined with example int. And you can even make it act as placeholders inside functions if you haven't written yet, if you want to. We could say func user ID for username string returns an optional int. I haven't written this code yet, so I'm going to do undefined for that username. And it'll work. It'll figure out to return optional int. It's great. Now, in this instance, you might think, well, if that's a placeholder for some code that I haven't written yet, I could just say fatal error. This isn't working yet. But in practice, yes, you could. Of course you could. But fatal error also has other meanings. Like you can have fatal error legitimately elsewhere in your code. And so when it comes to finding and removing the undefined instances later on, it's very easy to look for undefined. This means it has to be replaced later on, whereas you might have other fatal errors doing real things in your code. You can even use it repeatedly. You could say something like, let timer be a new timer, and give it loads of values. Here you can see there's like time interval. I don't know, it's undefined. Target undefined. Selector undefined. User for undefined. Repeats undefined. I don't know. I'll come back and fill those in later with real values. And yes, you could put in magic numbers. You could put in, I don't know, let's just guess true for now. Or I don't know, let's just guess time interval 0 for now. You can totally put in magic values instead, just like you could use fatal error. But the magic of undefined is it'll crash as soon as it's touched. It will call fatal error as soon as that code's actually used. Whereas a time interval of 0 repeats true, you might forget was just placeholder code. You might forget to come back to it and fix it later on. And the magic, therefore, is that undefined only works at compile time. It's a compile time hole filler, a compile time placeholder. It'll definitely crash your code at runtime, which is really nice. It just helps you push your code forward, get your project moving before you go and fill in all the gaps, which is really, really nice. Now, of course, you may have the question, if undefined t is not a phantom type, which it's not, what is it? And to be honest, I had exactly the same question. So I went back to the source and asked Johannes. Here's what he said. I wouldn't call undefined t a phantom type because, first of all, really it's a value. Well, a value that will never generate, but still. Even calling t a phantom type isn't quite right. T can be anything, so it could be a string, which is far from a phantom type. I think the closest somewhat correct term I have for this is that it's called the bottom value, usually written as an uptack. And even that is probably not right because the bottom type is defined as not having values. So the term bottom value isn't great either. So I guess we could say undefined return type is bottom. I love that answer from Johannes because it shows just how nuanced the discussion is. Anyway, that finishes up our discussion about phantom types. You've seen how they work, why you'd want them. I've given you practical examples galore to try them out. We even tried that experiment from Surush to build a state machine entirely with these things. And I even showed you how the undefined t function acts as a general placeholder for our code while we're still working. It's not a phantom type, but it's still fascinating. Thanks for watching this video, folks. Again, this was a free sample from Hacking with Swift Plus, a subscriber-only area on my site where I post lots more videos like this one, all in 4K Ultra HD with massive articles attached, code samples and more. For more information, check out this URL, hackingwithswift.com/plus.